Okay, in this video, we're going to look at finding surface area using double integrals. But before I give you the result, which is pretty similar to the surface area results you've seen before, where you have a square root of 1 plus dy over dx squared and you integrate it. With this particular drawing here, I just want to show you why this is different from the other ones that we've done. So what's really happening here is we're going to have a surface, right? We're not finding all the surface, like entire surface area. We're trying to, suppose we want to find the area of just this particular bit of this surface, right? So we're not finding the entire surface. It's just like this part of the surface. What we do then is we sort of project this down into the xy plane, and this will look like a triangle. Or equivalently, you can think of it as a question can be given as, here's a surface and here's a region D on xy plane. If I take this region up, right, if I extend it all the way up, it's going to curve some shape on the surface. That's no more going to look like a triangle. In this case, it's a triangle, right? And you want to find the surface area of that sliver, of that section. And that's when we use double integrals. Because remember, for double integrals, we're always like projecting up from the plane. So I'm just going to give you the result, the area of the surface. So if you have z equals f of x comma y, that's a surface. Xy belongs to region D, where f sub x and f sub y, these are the partial differentials, are continuous, is given by the area of that surface as on the region. So we're not finding the entire surface area, it's for a given sliver of the region, is square root of, you find the x partial, you find the y partial, plus 1, and you find this double integral. So this is, recall from Calc 1 or maybe Calc 2, is the arc length formula, which goes a to b square root 1 plus dy over dx. And then for area, you just go like, so this is where this comes from. Instead of dy over dx, we now have the sum of the two different partials. Okay, let's look at an example. And that's probably the best thing to do, is find the area of z equals x squared plus 2y plus 2. That lies above a region T, which is a triangle with vertices 0, 0, 1, 0, and 1, 1. Right, so as with all double integral kind of problems, first I'm going to find out where this region is. So 0, 0, 1, 0, and 1, 1. So it's a right triangle of this form. Now imagine this is on your desk, right? In the perspective form, it looks like that. And then above is some surface, and you're projecting it up, and it's going to have some shape. And we're trying to find the area of this particular shape. So keep that visual idea in mind. Even though the second part of the visualization is not required, but so here we have our surface is pretty straightforward. It's x squared plus 2y plus 2, which means its partials are pretty straightforward, 2x and 2. So the area is going to be the triangular region T, square root of 2x squared plus 2 squared plus 1, and we have the A. Now we're left to to find the limits in this triangular region that we have, we will use the method that we use for the general method. Right? So you can either go x first or y first. Here, let me go in y direction first. So if I'm going from here to here, I'm going to need the equation of this line. Now this equation is just y equals x. As you can see, the slope is 1. So this is 4x squared plus 5. And if I go dy first and then dx, y goes from 0 all the way to the line y equals x. So it's 0 to x, and x goes from 0 to 1. Since the first integral is with respect to y, this becomes x square root 4x squared plus 5 dx is 0 to 1. And now this can be done using u sub. Because if I sub in u is 4x squared plus 5, I get du is 8x dx, and I get x dx is 1/8 du. Limits: when x is 0, u is 5, and when x is 1, u is 4 times 1 plus 5, which is 9. So I get 5 to 9 du over 8 and square root of u. So u to the 3 halves times 2 thirds. There's also an 8 and 5 to 9. So I get 1/12. 9 raised to 3 halves minus 5 raised to 3 halves. And we can do that. Square root of 9 is 3, and then 3 cubed is 27. And square root of 5 times square root of 5 times square root of 5 is 5 square root of 5. So this becomes your surface area above, projected upwards in that direction. And that's pretty much it for surface area. And also for this particular module. So the remaining videos will be posted in the next module, where we will talk about triple integrals. So we're done with double integrals now. The next thing is triple integrals, as well as a couple of different coordinate systems in which we can evaluate triple integrals. All right, that's it for this video. Thanks.